All right, we're going to get started here with our notes on page 29. So looking at this section of our text, we're talking about distributions and the way data can be spread out. So there's a few different vocabulary terms we need to review here and associate them with their graphs. First off, if data is symmetric, symmetric is a term that should be familiar to most people, that it's talking about the left side and the right side of the distribution basically being the same. So it's not going to be perfectly like a mirror image, but it's going to be mostly the same along each side of this curve. A normal distribution is an example of that. So it's not skewed to either direction. We'll get to skew in a minute. The mean and the median and the mode are all basically the same. They're right in the same general part of the data. But a normal distribution is going to be shaped with a tail on each end and a peak in the middle. So if data is skewed, it ends up having a tail to one side of the peak. So when it's skewed left, the tail is over here to the left, and when it's skewed right, it means the tail is over here to the right. And that'll occur when there are outliers in the data set that are way below the rest of the data, in the case of being skewed left, or way above the data when it's skewed right. So if you ever see a tail on the data, whether it's on a bar graph like this, or on a dot graph, or however it's being displayed, the tail is going to indicate a skew. Now, in this case, the mean and the median will not be the same, because you're going to have a lower value attached to the data set when it's skewed left that pulls the average down, while the median stays where it is, and when it's skewed right, the outliers are higher, and so they pull the average score up and makes the mean higher than the median. So whenever you have a skewed graph with a tail, it's going to make these mean and median not be the same. All right, bimodal, it doesn't happen very often, but bimodal means two modes, essentially. So there's two peaks to the graph. There's two central areas on the bar graph. So bimodal is when we have two different centerpieces, so to speak, on a graph. They can be symmetric, can be asymmetric. That is not something that's characteristic of all, but this is the general shape of a bimodal graph. When something is uniform, it's like when you get on the exercise bike or the treadmill and you set it to be the same the whole way through. With no peaks or valleys, it's just going to be basically the same all the way across. So it is symmetric, it is equally distributed, and the mean and the median would be about the same. All right, so looking at the graph on the bottom here, the histogram is showing how much student debt is held by a representative sample of 457 borrowers. So the amount of debt in thousands is along the bottom. You kind of have to squint to see it, but it's in increments of 50. And that's 50,000 all the way up to 300,000. And going up the side, it's the number of people who responded that way. So there are things to note here, and I'd like you to write these down as notes in your margin as well. The direction of the skew is the side with the longer tail. And so this one has a tail to the right, which means it's skewed right. When that happens, the mean will be larger than the median, because that larger value will affect the average more than it affects the center point, right? So if you have a really high number, it's the last number either way, so it doesn't affect the median, but it is a much larger contributor to the average score, so it does affect the mean. And it's going to be the other way around when the data is skewed left, because the data would pull the average down, so the median would be bigger. So just write those things down so we can refer to them. And you can pause if you need an extra minute. Okay, so then on page 30, I've just recopied this graph so you can flip back to it. But she says the distribution is skewed right because there's a tail of borrowers with very high amounts of debt, which is accurate. We can see that here. So therefore, I know the median must be greater than the mean. And we just talked about that. So the median is not going to be bigger than the mean here, because when I go to add up all the data points, adding those large values is going to have an effect on the average. It's going to pull the average up, which is the mean. But it isn't going to affect the points in the order that they're in. So her conclusion is incorrect. The data is skewed right because the tail's extending to the right, but that right skew means the opposite of what she said. The outliers are on the right, which increases the mean without really affecting the median. All right, so anytime we're explaining something here, just pause the video so that you can write down what you see. All right, so moving on, sketch the approximate box plot that you think would represent this data set. Since you don't have the exact data set, your goal is to summarize the overall distribution with a box plot and not calculate the exact values. Okay, so it looks like most of this data is down on the left side here. So our middle point is not going to be the middle of the x-axis. If you think about how a median works, we don't have nearly as much data to the right of 100,000 as we do to the left. So our middle point, if we were to do this with a dot plot, would be way lower than what the mean would be. All right, so the thoughts are, some people have no student debt, and some have hundreds of thousands, but most people have between 10 and 50,000. And that checks out on this bar graph. If you see where the taller bars are, they're down towards 0 and in between 0 and 50,000. So that interpretation makes sense by the shape of the graph. So if I'm trying to do a box plot and I'm going from 0 to 300, I'm going to put the median somewhere in the lower values where most of the data lives. And I'll have a minimum. Minimum would be 0, maximum would be 300, because I did have a respondent in the bar graph that said 300. So this is, take a shot at drawing that box plot. You can pause here and do that, and then come back and we'll see how it should look. All right, so here's an example of how that box plot would look. And what we should have, and I didn't put it on here, but we should have a line on either end too, indicating where the min and the max are. So we should have one at 0 and one at 300. And then the bulk of the data, this is the middle 50% of the data, all falling within this box. The bottom 25% of the data here, so that's 75% of the data, all under 50,000. All the rest of this makes up only 25% of the data because it's only one component of the box plot. So that upper 25% is really spread out, but the bottom 75% is very condensed. Okay, so we've learned how to measure the spread of data using range and IQR. Standard deviation is another way we can do that. And what that measures is how spread out the data is compared to the mean. So you'll see this in many different ways. You'll see it written as SD, as STD, DEV, as for abbreviating standard deviation, or there's this symbol called sigma. And you should practice drawing this because it's not that easy to draw at first. It kind of looks simple, but it's really not. So you're going to start and make a circle down and back around, and then just make a tail out. So practice drawing that so you have an idea. If a graph has low standard deviation, that means that it's not, deviating means going away from what we expect. So if we have a low standard deviation, then the data points are basically clustered around the center. So there's an example of that graph on in this first section here. If the mean is at 50, according to this data, here's 50 on the graph. It's a little hard to see, but 50 is right here in the middle. Most of the data is between 40 and 60. So this is a low standard deviation because most of the data falls very close to the mean. A high standard deviation could look like either one of these, where a lot of the data is significantly away from the mean. And so you see that when you have a flatter graph, because it's pushing more of the data out to the edges. Whether it's skew left like this or whether it's a normal curve, either way, it can have high standard deviation if we've got a lot of data on the edges. So those are the shapes that you're looking for when you're trying to determine that. Data sets that don't follow normal tend to be higher standard deviation because you got that tail pushing data off to the ends, whether it's to the left or to the right. Okay, so those are your definitions for standard deviation. So the next page, if you go over to page 31, it says to sort these histograms from lowest to highest standard deviation. So I've got these in number form here, and you can see, hopefully, justify why that would be. The number one ranking lowest standard deviation is the one that is the steepest in the middle, because all the data is almost in a column here, clustered around the mean. The worst one, or the highest standard deviation, the most spread out, is this one here, where it goes all the way to the edges. And then in between you have these two. I would classify histogram C as a second lowest standard deviation because it's pretty clustered here. Not nearly as much as the first one, but more so than the other two. So that's how you generalize your characterization of standard deviation. So how would removing an outlier impact the standard deviation? So let's first remember what an outlier is. An outlier is something that is on the edge or beyond what you would expect in a data set. So if you were to take a really high number away or a really low number away, it's actually going to cluster the data more. So it's going to reduce the deviation because the data is going to be less spread out. Right? So if you pull a high number out, all the remaining numbers are going to be more clustered than they were with a high number in. Same thing with a low number. If you take a low test score out of a class, then the rest of the scores are more grouped. So taking an outlier out will reduce standard deviation. Okay, so if we were to survey all the students in your grade, whether you're 12th grade or 11th grade, doesn't matter, which research question do you think would yield the data with the lowest standard deviation? All right, so we'll talk about, you can write down these correct answers if you wish right now, but if we look at each one of these and examine each one, how tall are you in inches? So people would respond probably between, I don't know, for upperclassmen in high school, probably between 58 inches, which would be just under 5 feet, and maybe 72 inches, which would be 6 feet, maybe 75 inches. You might get some tall people responding, but that's not that large a range. So, and the data is likely to be centered around 5'7", 5'8", somewhere in there. How old are you? That's going to be even more clustered, because if we're talking about just your classmates, there's not going to be more than a couple years difference, right? But in the inches, if we're talking about how tall in inches, between 48 and 75, that's a fairly decent range. Usually, if we talk about siblings, some people might have one, some people might have none, but we're probably not going to have more than 4 or 5 for most people, so not going to be a terribly large number of siblings. How many minutes does it take you to get to school? In a school district as big as ours, that can really vary. So letters A and D would have more variation in the responses and therefore a wider range and pulling answers further away from the center, where ages are going to be much more centered, and so would siblings. Okay, so that takes us through the end of page 31. Let's go over to page 32 and look at an example of what you're going to be expected to do on your own in a few minutes here. So, histograms for student loans, housing, and high-cost lenders is the title of this application. So, federal student loan balance by age. That tells me right here that it's going to compare student loan balances against how old people are and how long they've had those loans maybe. So we're looking at a histogram on the left showing balances of borrowers that are under 25, and then on the right, more middle-aged, between 35 and 49. And it's a sample of 100 borrowers in each case. So the sample would have been taken randomly, so pulling from different demographics, but all within the same age group. So if we look at the x-axis, we can interpret what's going on here. This is the amount of money of student debt. And because the histogram, we're looking at categories. So each of these bars would represent a different bin of finances. So if it's from 0 to 50,000, maybe this is 0 to 10 or 0 to 15. And then another bundle from 15 to 30 or something like that. So on the left side, we see how many people responded. We're at 75 people. Now we're at 21 people or so, and then we're way down here. Whereas when you're over 35, now there's not as many people reporting low debt. There's more people reporting high debt, which is interesting, right? It's interesting that the older people are reporting high debt. So the summary, how does student loan debt compare for borrowers aged 35 to 49 and borrowers below 25? So you could comment on how we have some much larger numbers on the older people and smaller numbers on the younger people. We could also comment on standard deviation, because the data is more clustered for the younger people. There's much more spread on the older people. We could mention about the smaller overall range, because there aren't any that are very large on the under 25 group, and there are several that are large on the other group. Mean and median will be smaller for under 25 because there aren't any data at the upper end pulling those responses over. Okay, so for each of the following statements, respond true, false, or can't be determined. Then write one sentence using math vocabulary and or numbers to support your response. So there's 2 statements here. Let's do these 2. We'll get to the other page in a minute, but do these 2 first. Pause here and try to write true or false for each and give a supporting reason. All right, so for A, the median student debt is higher for borrowers aged 35 to 49 than borrowers under 25. So let's remember what the median is. If we were to lay all 100 responses for each category, end to end, we're looking for the 50th and 51st responses. We want to know right in the middle. So is it true that the median is higher for borrowers 35 to 49 or for borrowers under 25? So it is true that it's higher for the over 35, because you can see far more data points of higher balance with that graph and far fewer in that first histogram bin. So I've only got about 50 people, not even 50 people, 45 people in the first bin with the older group and 75 people in the first bin. So if there's 75 in this first bin, numbers 50 and 51 must be in this section. But numbers 50 and 51 would be in the next section on the older people, so you can tell that way too. All right, for part B, standard deviation of borrowers under 25 is higher than that of borrowers over. So we just talked about that actually. It's false because when you look at the 25 and under graph, it is narrower, so things are more clustered and less spread out. So that would be a smaller standard deviation for that group. All right, go on to the next page and look at those two as well. There was one borrower aged 35 to 49 with a loan balance of exactly $300,000. All right, I got to go back to the graph and look at that here. So 300,000. We've got a couple of numbers of tiny little bars here, 300 and 350. So we want to know if there's one borrower with a loan balance of exactly 300. That's actually a drawback of a histogram, that we know that they fell in a range of responses, but we don't know exactly what that response was. So we can't determine it. The histogram bin is covering a range of values from one thing to another. So they fall in there, but we don't know exactly what that value is. And the last one, for borrowers aged 35 to 49, the mean balance is greater than the median. So think about what skew does. The second graph was skew right. There were higher numbers to the right. So does that raise the mean or does that lower the mean? Well, if we're adding higher numbers in, it must raise the mean, which would take it above the median. Anytime a graph is skewed right, the mean is higher. So the mean will be pulled in whatever direction the skew tail is, whether it's to the right going higher or to the left going lower. All right, last one here, in inference, which is a conclusion we can draw. Why is the mean student debt higher for borrowers aged 34 to 49 than borrowers under 25? It's actually 35 to 49. So this is like right at the beginning of this section where I was explaining that we have those really high numbers for the older people. Why would that be? So if you take a second to write something down here, make your best guess as to why that might be. All right, so this is a theory, possible theory. Older borrowers have had more time to incur debt for higher degrees, like a master's degree or a PhD, which is more expensive. Maybe they went to medical school or law school or something like that. Whereas those younger borrowers are probably not at that step yet or they could be, but not necessarily as likely to be going to those higher degree programs that would make them take on more student debt. So maybe we're looking at undergrad only with under 25 and the higher degree programs for the others. So that's a possibility. All right, for level 2, this one you're going to do on your own. So using the template from the last example, you can just use everything we just covered. You're going to complete the rest of 33 and page 34. This is talking about mortgages. So we have Michigan mortgages and Michigan rents. And it shows you how much you pay per month for each on the bottom. So this says, for example, over 100 people responded that their mortgage or their monthly housing payment for their rent is between $500 and $1,000. And this one shows about 70 people responded that their mortgage payment is between $1,000 and $1,500. As an example, that's how you would read this. So you're going to go through all of these questions on 33 and on 34, and then you're going to go back to Google Classroom, and you are going to find exit ticket 8.4, and that's where you'll enter your answers, and that's what will be graded. So you can work through that on paper first, and hash out the answers that you want, and then go on to there. Do your best with that, and that's it.